So you have a growth rate associated with the population, okay? But it cannot increase to infinite value, right? Why not?
Initial was big, might be random, sir.
Yes, correct. So because of the limitations of resources and other factors like disease, environment, evolution, there will be a death rate. Okay. So the growth cannot be infinite. Even if there are no diseases, there are limited resources. Okay. So when you have only 2 rabbits on an island, they are happy to reproduce and they will produce more because there is ample amount of resources available for them to feed. Okay. And then they will keep on doing it, and then there will be a limitation on the resources available, so they cannot migrate, so there will be death, because not all of them will be getting the food required. This is what you also see with dogs here in this campus, right? Also outside the campus, right? So there is a growth rate and there is a death rate. Okay. So if I have to say that in the nth plus 1 generation, the amount, so the number of population, I can write it in various ways. I can write it in different equations, and one of the equation would be to multiply the growth rate, which is r, with xn into 1 minus xn. So xn is the population in the previous generation, okay, and 1 minus xn factor is trying to balance it by counting the death rate. Okay. So this equation will simply look like this, a parabolic equation. So the population will increase to a maximum and then it will start decreasing. It depends on growth rate. What is the growth rate? Okay. So you take this equation and give some value of r to it. So 0.2, let us say. Okay. And then you will see that for a very small value of growth rate, the population will increase to a value and then it will decrease and it will become extinct. Okay. So if you plot the growth rate r and then you plot the population xn, equilibrium value of population. So it will increase and then it will become extinct. Okay. If you increase the value of r, in that case also you will have similar phenomena, but then the curve will come up a little bit, and for some values of r, it will become stable. It will become stable, it will not change. It will not decrease. It will also not decrease, it will also not decrease. It will obtain an equilibrium. Okay? Is this okay? And so if you change the r value, so r value to any other value, or the initial xn value to begin with, you cannot start with 0 because there will be no reproduction in this for the case of population. So if you increase with some value of xn, these initial parameters will not change much the overall effect. So only this part will change a little bit, but it will obtain the equilibrium. Okay. And then you keep on increasing r, and you will hit a value of r where you will see a different phenomena. And what will happen is that this curve will, so let me recall, so then I have to plot another graph. So you have to do this kind of calculation for different values of r, and you have to find out different equilibrium values of xn. So for example, for this particular value of r, you have this curve which is getting equilibrated at this value of xn. Okay, so for different values of r, the curve will be saturating at different values. You take those values and then you plot it. So you plot r on x-axis and then you plot the equilibrium or saturated value of xn. Okay. So here I don't think this is xn. I think it is n, the generation. As the generation increases, it saturates. Okay. So then you take r and xn and then you plot it. So for initial values, for a very small value of r, the population will be extinct. There will be no population. Okay, and then as r increases, the population will start increasing. So your equilibrium value, the saturated value, will increase with increasing r. Okay, do you follow what I'm saying? So you begin with 4 rabbits, and if the value of growth rate is 0.3, then you will have, let us say, 1400 rabbits after 100 generation, and this number will not change. Okay, so it will not be 1400 exactly. It can be 1401, 1405, 1395 and so on, but it will be very close to that. Okay, as you increase r, so you go to 2.0 value of r, then instead of 1400 you will have a value of, let us say, 15,000. Okay, so the saturation value will increase as you increase r, but it will saturate to one single value, and that one single value are these values. So for this value of r, you have this value of saturation. Okay, and how long you have to do that iteration on n? You have to do that as long as xn plus 1 minus xn is very small. That's how you find out the saturation. Right? So if you keep on doing this, it will keep on increasing, right? And then there will be something different. What will happen? It will bifurcate into 2 curves. Okay. So on this plot, what you will see, that for some value of r, it will, instead of saturating at one value, it will be oscillating at 2 values. In one year, the population will be larger. In another year, it will be smaller, and next year larger, another year smaller, and so on. Okay. So there will be 2 saturation points. And what will happen beyond that? So as you increase the value of r, these 2 points will go on separating with each other, and then there will be further bifurcation. Okay. So then this curve will look like it is going to one value, second value, then third value, then fourth value, and it will be oscillating like that. So it will have 4 saturation values. Okay, and again, and there will be a value of r where it will be completely chaotic. What does that mean? It means that, and that particular value is 3.57 for this equation. For this particular value of r, what will happen to this curve? At every point, it will have some value which will never be repeated, and it will be completely random. So I shouldn't say never be repeated, because that is against randomness. But you can't say that it is saturating to one value, or 2 values, or 4 values. It will be a random thing. Okay? It will never be saturating to one value. It will be completely chaotic. Okay? And so this curve will bifurcate into many beyond this point. Okay? And what will happen after that? It will be chaotic? No. After a certain period of time, there will be again a period of order. For a very short period of time. Then there will be again chaos. Then there will be again order and chaos and order. And after that, what happens, I do not know. Okay? So with this algorithm, the random number were also generated in computer codes. But knowing the initial value and the equation, you can regenerate the numbers. So they are called pseudo-random numbers. Okay? They are not really random numbers. I don't know if there is any algorithm right now which can really generate a complete random number for computers. So, okay, that part is okay. So this is how it looks like. And there is another interesting thing about this is that this part is similar to this part, is similar to this part, and that is not similar here. And so there is, for a certain period of time, you have a symmetry, a self-symmetry at different scales. Okay? And if you rotate this curve, if you rotate this plot, then you will see, and that I cannot draw very nicely, but it looks something like this. So you have so I'm just drawing a Persian dome or something. So, and this is also on the other side. I have just drawn the half side. So do you know what this is? Because I have not drawn correctly. But okay, so we have internet, so I can show you that. Do we have internet now? Can you see the picture? I was trying to draw that and I have failed to draw it. This diagram. Okay? And this diagram tells that any point within this will not be chaotic, any point beyond this will be chaotic, but I'm not too sure about it now. Okay? So the R values which are here, they are not chaotic. Okay? So so I believe it may be like this, that the numbers inside this are non-chaotic and outside that are chaotic. Okay? So what is this? This picture? Have you heard of Mandelbrot? No? So he has written a book on fractals and on self-symmetry. Okay? And so if you magnify this and look at on this part, that is exactly a replication of the total figure. And then you magnify that, because that will also have a tip. You have a tip like this, you have a tip like this. When you magnify and look on this one, so for example this one, you also have a tip there. Okay? And then you magnify on that tip, you will again have a tip, and there is no end to it. Okay? So this is called self-symmetry, and this is shown in convection when you have flow of fluids. This is also found when you have water dripping from your taps. Okay? And you can change it, and you can do this at your home. And whatever I'm talking today is already there in a video, and that you can see very nicely explained by someone. So, for example, you open your tap a little bit, so then you will have this dripping sound, tip, 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 tip. So you have maybe 2 saturation points, and then you open it a little bit more, and tip, 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 tip. Okay, and then you will reach a rate where it will be chaotic. Okay, so there, all that dropping droplets will not be at particular point of interval will not be same. Okay, and then it will again reach an order and so on. So this kind of phenomena has been found in many places. Also probably in materials, also probably when you fracture a surface, maybe you see something like this. Maybe there is an order in chaos also, and there is a chaos in order also. Okay, and one particular thing is that the geometry of this differs, and it is not particular about this equation. So this equation and similar equation were also used by the fashion designers. Okay, so before that, the fashion used to be like you have check shirts and squares and circles and leaves and things like that. But then when this fractal came, some of the fashion designers picked it, and they just ran this algorithm and created this Mandelbrot and similar kind of structures, and they started printing it, and people were very happy about wearing a printed shirt in Goa or some beach, these kind of. Then this algorithm of fractal was also used in computer simulation, and that guy just read the book of Mandelbrot, applied it in simulating the mountains and other things, and somehow he applied this, and he made a lot of money out of it. Okay, so that should be your motivation. Okay, and fractal has been also applied in fracture. Okay, so quantitative fractalography, we have seen fractal dimensions, we have seen self-symmetry. Okay, so you can maybe think about it, and you can take any equation which shows a hump. For example, sin x will also show you not exactly that behavior, but a different self-symmetrical pattern, a different approach towards chaos. Okay, so somebody measured this and that, and the ratio of that, and that ratio was found to be same in all the fractions. So you take smaller fraction beyond that, and you find exactly same value, which is 4.336 or something, always same. So there is an order in chaos. That's it. So you think about it, maybe try to apply somewhere or not. Try to see some of the events on which you are doing your PhD. Maybe there is some chaos, maybe there is some pattern.
So this can be also visualized like that in photo multiplied जैसे इलेक्ट्रॉन का एवलांच इफेक्ट होता है, उसमें भी नहीं होता है, एक दो जनरेट करते हैं, then
Yes, also maybe in uranium radioactive decay. I am not so sure of it, but maybe.
So उसमें limitation होता है like energy loss.
So Navier-Stokes equations, which some of you might have seen in the presentations. So the problem with those kind of equations are that a minute change in the initial condition. So that probably was not explained in some of the presentations. And I'm also not an expert on Navier-Stokes or fluid mechanics, but a minute change in the initial condition can create a very large and amplified change in the result of the solutions of Navier-Stokes. So there is no general solution to it, because it is not deterministic. If you and that is called butterfly effect. Why it is called butterfly effect?
Sir, very small change will produce big effect.
Yeah, but why butterfly? How is
Sir,
butterfly related to this?
So there is a concept that at some place, if butterfly moves its wings, so that produce a circular effect in air, and which causes a big effect at somewhere.
Correct. But there is more to it. So there was a paper published by this name, butterfly effect, and from that paper it got famous. But so, for example, when Newton was trying to solve the equation for sun and earth, rotation of earth around sun like a pendulum, so he was able to solve this very easily. But Newton has reported that he got headache, alleged reporting that he got headache while solving three body problems of, and even that problem is there with the pendulum. So if you have a pendulum, okay, so this pendulum is moving like this on xy plane, and wherever it is moving, okay, so you plot it, so it will be something like this, an ellipse if there is no damping, okay, and if there is damping, then there will be a spiral, and then it will come back to the center point, okay. This is known, this is predictable, this is deterministic. Why? Because you change your initial conditions, you put your pendulum anywhere, you will always get this plot, always, it will never deviate from this, okay. But you include one more component to this, another pendulum, okay. So then this pendulum goes there, another component is here, and this is also swinging, that is also swinging, and then you try to plot that. That becomes a chaos. There cannot be a solution to that, okay. But in some cases, the plot also looks like a butterfly. That you should check out on internet. So maybe if it's there. You see this plot I'm talking about. So I will not explain it because I also don't understand it much, but I don't know this plot is within what. So that you have to check out. And they also talk about this thing, the pendulum and three body problem and whatever I have said. So it looks like that. Okay. That's it.